Hello, everyone. My name is Prabhasha, and I'm part of Passionate Minds. And today's lecture is going to be focusing on nomenclature for SCH3U, grade 11 Chem. All right. So, nomenclature is basically the naming system for chemical compounds, formulas, ions, and etc. When you're writing out a chemical formula, you need to know the elements in the compound and the number of atoms that are present for each element. Typically, the valence or the oxidation number is looked at when creating formulas. And the oxidation number is basically the number of electrons that are to be gained, lost, or shared in a compound. In ionic bonds, the valence will tell you the charges on ions. Basically, the atoms before group 4 will donate the number of electrons that they have in their valence shell. So, for example, aluminum has a charge of +3, magnesium has a charge of +2, sodium has a charge of +1. This means that aluminum is going to donate 3 electrons in an ionic bond, magnesium will donate 2, and sodium will donate 1. Atoms between groups 5 to 7 will accept electrons to make a full shell. So for example, nitrogen will have a charge of -3, which means that it'll accept 3 electrons. Oxygen has a charge of -2, accepts 2, and fluorine will have a charge of -1, meaning that it'll accept 1 electron. In covalent bonds, the valence indicates how many electrons the atoms will contribute to the bond. And there are atoms that have different valences. So for example, tin, mercury, cobalt can have more than one valence. To give you an example of tin, it can have a charge of +4 or I believe +2. And mercury, I believe, has a charge of +1 or +2. To just show you a bit more of what I was talking about earlier, groups 1 and 2 and 3, they donate the number of electrons that their valence has. So anything in group 2 will donate 2, group 3 will donate 3, group 1 will donate 1, and groups 5 through 7, so 5, 6, 7 will accept 1 electron, 2 electron, or 3 electrons. When we're looking at transitional metals, so metals could have one or more oxidation states. For example, mercury, it could have a charge of +2 or +1, +3 or +2 for iron. Copper is +2 or +1 as well. Magnesium has +7, +4, and +2. And this is why the nomenclature or how you name each compound is extremely important, so people understand what valence you're specifically referring to when you're naming a compound. All right. So for binary ionic compounds, the steps to naming them and forming the compound are writing out the symbols with the less electronegative atom being first, the metal, and then you write the more electronegative atom after that, the nonmetal. You write the charges as you found on the periodic table. We'll be going back to that quite a bit. We're going to do a crisscross method, which I'll show you in the next slide, and we're going to reduce as much as possible, and I'll show what this means as well. When you're naming the compounds, write the metal first and then the nonmetal, and then you drop the ending of the nonmetal and add "-ide" to it. So for example, the metal is capitalized, but the nonmetal isn't. Sodium chloride, right here, chlorine is an atom here and sodium is atom here. We drop the ending, so the "ine", and then you add "-ide" to it. Alright, these are some examples that I just created for you guys. Magnesium sulfide. Magnesium has a charge of 2 plus, so sulfur has a charge of 2 minus. So when you crisscross, the 2 of sulfur is going to go here, and the 2 of magnesium is going to go here. Then you want to reduce to the lowest possible terms. So since you have 2 magnesium ions and 2 sulfur ions, these can both be reduced to 1. You want to go down to the lowest possible number of atoms for each element. This is why magnesium will have 1 atom, sulfur will have 1, and you'll create the compound magnesium sulfide. Notice in the capitalization as well, magnesium is capitalized, but sulfide isn't. This is going to be a recurring theme for any of the compounds where the first word is going to be capitalized, usually the metal, and the second word isn't, usually the nonmetal. Alright, we'll take a look at lithium chloride next. Lithium has a charge of 1 plus, sodium has a charge of 1 minus. When you crisscross them, you get one for lithium and one for chloride, so you could just indicate it lithium chloride like this. You don't have to put the numbers if they're 1. And like I said before, you drop the ending and add IDE. Lithium is going to be capitalized. Aluminum phosphide is another compound that we can take a look at. Aluminum has a charge of 3 plus. Phosphide has a charge of 3 minus. Aluminum will have 3 atoms now, and then phosphide will have 3. And these can both be reduced to 1 because you have 3 of aluminum and 3 of phosphide, which makes ALP. And like before, aluminum is going to be capitalized, phosphide isn't. Sodium chloride is another one we took a look at earlier. Sodium has a charge of 1 plus, chlorine has a charge of 1 minus. When you do the crisscross, they both have 1 atom each, which means that you don't have to show the number of atoms in each element. And this is also another word for salt. Salt is what sodium chloride is. Alright. Now when you're taking a look at multiple valences, this occurs with transitional metals that have more than one valence. Some examples include tin, iron, copper, mercury, and just check the periodic table if you want to be sure of all the atoms that have different charges. The compound formula is going to be the same as the ionic binary, so we're going to be doing the crisscross method. And if the charges don't cancel out to 1, like as they did for the binary, because all of these are 1, this occurs when you have charge of 1 plus and 2 minus, basically when they can't cancel each other out. We're still going to do the crisscross, but we're going to have to write the numbers in if they're above 1. And when you're naming something with multiple valences, we're going to be using Roman numerals to represent the charge to indicate the valence electrons present. So, to give you an example, iron has charges of plus 2 and plus 3. If we're using iron with a charge of plus 2, it'll become iron 2. And iron with a charge of 3 plus will become iron 3. Non-metal naming is going to be the same, just add the "ide" at the end. Alright, these are some 3 examples. Copper 2 fluoride. Copper has a charge of 2 plus and fluorine has a charge of 1 minus. When we do the crisscross, we get 1 atom for copper and 2 atoms for fluorine. We'll take out the 1 and it'll just be CuF2. When we're naming it, we add the 2 because we're using copper with a valence of 2 plus. If it was the other valence, copper 1 plus, then we'd do copper 1 and it would just be CuF. When we're taking a look at iron 3 chloride, iron has a charge of 3 plus, chlorine has a charge of 1 minus. When we do the crisscross, iron will get 1 atom and then chlorine will get 3. This indicates FeCl3. And since we're using iron with a charge of 3 plus, we use iron 3 or 3 I's to indicate the valence of iron, chloride. Finally, we're looking at tin 4 oxide. Tin has a charge of 4 plus in this situation, and oxygen has a charge of 2 minus in this situation. When we crisscross, we get SN2 because there's 2, the valence is 2 minus for oxygen, and then 4 for, the valence is 2 for oxygen and 4 for tin, so SN2O4 is what we get. And since 2 and 4 can be reduced because you can divide both by 2, you get SnO2. Just divide both of these numbers by 2. When we're naming it, we use IV to indicate the Roman numeral for 4 because the charge of tin is going to be 4. Alright. And just a quick tip when we're doing anything with nomenclature, the best way to understand these is to keep practicing them. Just do a bunch of examples like what I'm showing you right now. Alright. Taking a look at when we're naming multiple valences, the Latin prefixes can also be used when naming multiple valence metals with 2 or more valences. Now, there's very specific names that you have to use when we're naming the following metals. For antimony, it's Stib, chromium is Cro, copper is Cup, iron is Fur, lead is Plump, and tin is Stan. These are the prefixes that must be used when we're using these specific elements. When we're using the suffixes to indicate the correct valence, we use "ik" to indicate a larger valence and "us" to indicate a smaller valence. Alright, now taking a look at the examples on the bottom for naming valence molecules. we'll take a look at FeCl2 first. Now, FeCl2, when looking at this molecule, we already know that chlorine is always going to have a charge of -1. Since there's two atoms of chlorine, that means iron has to have a charge of 2 plus. And since 2 plus is the smaller of the two valence charges of iron, it can have a charge of 2 plus or 3 plus. This means it's going to be the smaller of the two, and it's going to be ferrous. As when we take a look at the slide before, we see iron is fair, and S is going to be the smaller valence. And it's going to be ferrous chloride. Looking at FeCl3. Now, Cl3, 3 atoms of chlorine, means iron is going to have a charge of 3 plus. Now, since this is the bigger of the two, we're going to be naming it ferric chloride because ic represents a larger valence. And we'll take a look at CuBr as well. Bromine's always going to have a charge of -1, and since the ratio is equal between the two atoms, this means copper is also going to be -1, +1, sorry, in this situation. And since copper can have a charge of 1 plus or 2 plus, this is the smaller of the two charges, meaning that it's going to be cuprous, as us represents a smaller valence. Cuprous bromide. All right. Now, polyatomic ions, these are ions that are made of more than one element or atom, but they behave as a single ion. The main ones are all going to be labeled on this chart right here, and I would personally recommend that you memorize this because teachers are going to be using this a lot throughout grade 11 chem, grade 12 chem, and even university chem. But the main ones are going to be bromate, bromite, chlorate, chlorite, iodate, iodite, nitrate, nitrite, hydroxide, cyanide, acetate, permanganate, bicarbonate, carbonate, sulfate, sulfite, chromate, dichromate, phosphate, phosphite, and sometimes ammonium as well. But make sure you know all of these as they are shown. Now, for the formula for naming and writing out the compound for polyatomic ions, the formula is going to be the same as before. We're going to be doing the crisscross method on charges, and we're going to be using brackets around the polyatomic ions if there's going to be more than one present. So for example, if we're looking at here, chlorine has 3 atoms for it, right? Now, when we're doing polyatomic ions, and if there's more than one, we're going to put a bracket around the polyatomic ion and write 2 or 3 or however many atoms we need of that ion. When we're naming these, we're going to be naming the metal ion as first, and then the polyatomic ion. If the number of oxygen atoms changes in the polyatomic ion, the name is going to change as well. So if the regular number of oxygens are present, the suffix is going to be ate. If there's going to be one less oxygen, the suffix is going to be ite. And then when we're looking at polyatomic ions and halogens, if there's more than one oxygen atom, we're going to add the prefix per, and then it's still going to be the ate suffix. If there's 2 less oxygen atoms, we're going to add hypo as a prefix and ite as a suffix. This might sound really confusing right now, but when we take a look at some examples, it'll all make sense. Alright, so I have a lot of examples here because this is this is an important concept to understand. We'll take a look at PO3 3- first. So, when we're looking at the polyatomic ion chart, PO3 is right here. The regular atom is phosphate, the regular ion, but since there's one less oxygen than the regular ion, we're going to have the suffix ite, and the name is going to be phosphite. We don't add hypo in this situation because PO3 will never go down to PO2, and we only add hypo or per if it is a polyatomic ion in a halogen. Right. Now this is another example that we'll take a look at. ClO3, chlorate. So the regular polyatomic ion is ClO3. This means that we're going to be using the suffix ate, and the atom is going to be chlorate. Polyatomic ion, sorry. Now, SO3 2-. The regular polyatomic ion is SO4 2-. Since it has one less oxygen, we're going to be using the suffix ite, meaning that this ion is going to be sulfite. Now, ClO4 is a bit special. The regular polyatomic ion is going to be ClO3. Now, since there's one more oxygen, we're going to be adding the suffix ate and the prefix per, meaning that this ion is going to be perchlorate because there's one more oxygen than the regular polyatomic ion. When taking a look at BRO minus hypobromite, the regular polyatomic ion is going to be BRO3. Since there's two less oxygens in the regular polyatomic ion, we add the prefix hypo and the suffix ite, meaning that we get the name hypobromite. Taking a look at NO2, the regular polyatomic ion is NO3, or nitrate, and since this has one less oxygen, we're going to be using the suffix ite, meaning that the name is going to be nitrite. Alright, now taking a look at some compounds with polyatomic ions. We have aluminum with a charge of 3 plus and phosphate with a charge of 3 minus. When we crisscross them together, we get 3 aluminums and 3 phosphates. Now this is what I meant when we put brackets around the polyatomic ions. And they both cancel out to 1, so it's just going to be AlPO4. The name is going to be aluminum phosphate. Taking a look at iron 2 chlorate, we have 2 plus as a charge of iron, and ClO3 has a charge of 1 minus. So we do the crisscross, iron gets 1 atom, chlorate gets 2 because of the 2 plus, meaning that this is going to be labeled as Fe bracket ClO3 bracket 2. And when we're naming it, we use Roman numerals to indicate the valence of iron 2 chlorate. Now, when taking a look at NaCO3, Na has a charge of 1 plus, and carbonate has a charge of 2 minus. This carbonate won't change, it won't have an extra oxygen. But when we do the crisscross method, we get 2 Nas and 1 CO3. If there's only one, we don't need brackets, so I take out the bracket in the next step and give you Na2CO3, sodium carbonate. Alright, now taking a look at lithium hypochlorite. Lithium has a charge of 1 plus, and ClO has a charge of 1 minus. When we do the crisscross, they're both going to have 1, meaning that they will cancel out. We don't need the brackets, and we get LiClO. Now, ClO has 2 less oxygens than the regular polyatomic ion, ClO3, meaning that the name is going to be hypochlorite, lithium hypochlorite. Alright. Magnesium perbromate. Magnesium has a charge of 2 plus as usual. Bromate with the extra oxygen will still have a charge of 1 minus. Once we do the crisscross, we get 1 atom for magnesium, 2 atoms for perbromate, and this is why we use brackets in this situation. Bromate's regular ion is BrO3. Since there's one more, we add per, and then the suffix is still going to be 8. Finally, the last example we have here is copper 1 nitrite. Copper has a charge of +1 in this situation as indicated by the valence, and NO2 will always have a charge of 1 minus, but there's one less oxygen than the normal ion, NO3. We do the crisscross method, we get 1 atom for copper, 1 atom for nitrite, so it's just going to be CuNO2. We use the Roman numeral 1 to indicate the valence of copper here, copper 1 nitrite. Now, binary compounds with hydrogen. If hydrogen is a less electronegative element within the compound, we're going to place it first. Now, if hydrogen is a more electronegative compound, we're going to place it second, treat it as a nonmetal, and then change the ending to "ide." The rules are going to be the same for crisscross and naming. To give you guys a couple examples of binary compounds with hydrogen, HCl or hydrogen chloride, H is going to have hydrochloric acid, but we're not learning about acids yet. HCl in this situation is hydrogen chloride. Hydrogen is less electronegative than chlorine, so the name is going to be hydrogen chloride. Sodium hydride is another compound. Hydrogen is going to be more electronegative than sodium, so we're going to be changing the ending of hydrogen to hydride. Name is going to be sodium hydride. For binary acids, the formula for this is going to be hydrogen will have a valence of 1. We're going to be doing crisscross to find the formula, and we're going to be adding aqueous as a subscript at the end to indicate the presence of water. this is how all acids are going to be defined. They're always going to have an aqueous as the state of that compound because it's usually solid, liquid, gas, but aqueous represents soluble in water, the presence of water, and this is present in all acids. When we're naming binary acids, we're going to be adding hydro as a suffix, and then we add the name of the nonmetal, and then we add ic at the end, and then we add acid as another word. I'll do a couple examples to show you what I'm talking about. So HF, aqueous, these three should have states of aqueous. Um, this is going to be hydrofluoric acid because hydro is going to be the prefix, fluorine is the nonmetal, we add fluor, and we add the suffix of ic, hydrofluoric acid. This is going to be with the state of aqueous, hydrochloric acid because we have chlorine here and we always add hydro. Looking at this, H2S, this is going to be hydrosulfuric acid. We add a hydro as the prefix, sulfur, sulfuric as in this situation, it doesn't follow the previous patterns, but sulfuric acid is how we name this, hydrosulfuric acid. Here is hydrophosphoric acid. We have phosphorus and hydrogen. We add hydro. We add the word phosphor, and then instead of ending it with us, we end it with the suffix of ic, and then we add the word acid at the end. Similarly, we take a look at hydrobromic acid. Bromic is going to be for the bromium. Hydro is going to indicate the hydrogen. And finally, hydroiodic acid. Hydrogen is indicated by the hydro. Iodine is indicated by the iodic. And again, all of these will have the states of aqueous in them to indicate that they are acids. All right. Now, when we're taking a look at bases, they're going to be creating hydroxide ions. Hydroxide ions are indicated by OH with a negative charge of 1 minus. We're going to be using the same ionic rules as before, and when we're naming them, we're going to be adding hydroxide to the end of the molecule and metal at the beginning. So, MgOH2 is an example. Magnesium has a charge of 2 plus, hydroxide has a charge of 1 minus. We do the crisscross, we get 1 for magnesium and 2 for hydroxide. And we always indicate hydroxides with this word, and they are OH in the compound. Now, we're taking a look at copper 1 hydroxide. Since hydroxide has valence of -1, and there's only one atom of copper here, copper is also going to have a valence of +1, meaning that we can also name it cuprous as it's the smaller of the two valences that copper can have. Looking at the next compound, iron 3 hydroxide. Iron has a charge of 3 plus in this situation because hydroxide has 3 atoms, and like indicated before, hydroxide has a charge of 1 minus. We can also name this molecule ferric hydroxide, as it's the larger of the two valences. Now, a more famous base, sodium hydroxide. Sodium has a charge of 1 plus, hydroxide has a charge of 1 minus. We do the crisscross, we get 1 for sodium, 1 for hydroxide. Aluminum hydroxide, hydroxide has 3 atoms in this situation because aluminum has a charge of 3 plus. And finally, we're taking a look at tin 4 hydroxide. There's 4 atoms for hydroxide in this situation because tin is going to have the larger of the two valences. Tin will only have an atom of 1 because hydroxide always has a charge of 1 minus. We can also name this stannic hydroxide, as stannic indicates the larger of the two valences. Alright. Now, oxy acids are characterized by the following formula. You have hydrogen, you have the nonmetal in between, and then you have an oxygen atom at the end. Polyatomic radicals are going to be bound to hydrogen. So, if the standard number of hydrogens are present in this atom, we're going to be naming it blank ic acid as the suffix. If there's more than one, if there's one or more oxygen, it's going to be per, go back. There we go. Per the nonmetal ic acid. If there's one less oxygen, it's going to be the nonmetal S acid. 2 less oxygens, it's going to be hypo the nonmetal S acid. Now, to give you guys some examples, H3PO4 is a good example. So, The standard name of this is just going to be phosphoric acid because hydrogen is present here. So since we have the state of aqueous, it has to be an acid. PO4 is phosphate. When we're naming polyatomic acids, we are going to be using similar rules to before. So we're going to be naming it phosphoric acid in this situation here. Now, HClO4. So oxygen, there's going to be one more oxygen than the regular ClO3, regular chlorate. So this is going to be perchloric acid because we have one more oxygen. Taking a look at HNO2. Nitrate's regular polyatomic ion is going to be NO3. So since there's one less oxygen, we're going to be using S as the suffix. So it's going to be nitrous acid. Nitrous. All right. Taking a look at H3PO2 now. Since there are two less oxygens within this acid, we're going to have to use hypo as a prefix. Phosphorus, S is going to be the suffix, and then we add acid at the end because there's two less oxygens. Taking a look at HBrO3, bromate has a regular amount of oxygens, so we can just write it as bromic acid. And then finally, HiO3 has a regular amount of oxygens, we can write it as iodic acid. It cut out here, but it would be iodic acid. If it was HiO2, it would be iodous acid. And if it was just HiO, it would be hypoiodous acid. Taking a look at these again, it's similar to polyatomic ion naming when we have one or more oxygens or one or less. Just a quick reference to go back to that. All right. Covalent and molecular compounds. These are going to be binary nonmetals that are going to be covalently bound. The crisscross method, as usual, will still be used. The naming is going to change a little bit. The naming is going to be, we're going to be using prefixes and then add the name of the nonmetal. And then we add another prefix and then we add the name of the nonmetal and we add "ide" at the end. The prefixes, these ones you will have to memorize. Mono represents one atom, di represents two, tri represents three, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. These prefixes is how we will indicate the number of atoms present for each element, for each nonmetal within a covalent compound. Alright, now taking a look at some examples, we have phosphorus, which has a charge of 5 plus, and oxygen, which has a charge of 2 minus. Once we do the crisscross, we get P2O5, and since P2, 2 represents di, and penta represents 5, we have diphosphorus pentoxide. So we treat the first nonmetal, the one with the positive charge, or the one with the positive charge, as the quote-unquote metal in this situation, where we write out the full name, but we do still have to add the suffix to it, the prefix to it, I'm sorry. And then the nonmetal is always going to be the one with the negative charge, and we're going to add oxide, and we add the prefix pent to represent 5. Taking a look at SO3, S has a charge of 6 plus in this situation. Oxygen has a charge of 2 minus. This is going to be S2O6. When we simplify them, we get SO3, sulfur trioxide. When we're doing nonmetals first, and if it's only one, so in this case, if there's only one atom of sulfur, we're not going to use mono in this situation. If it's anything above 1, so 2, 3, 4, and so on and so forth, we will. But for the first atom, if it's a nonmetal and if it's only one atom, we're not going to be using the prefix mono. So another example of this is carbon dioxide. Carbon has a charge of 4 plus, oxygen has a charge of 2 minus. We do the crisscross, we get C2O4, or simplify it and get CO2. We don't use mono here, we just write carbon and write dioxide after that. Taking a look at NO2, nitrogen dioxide, there's 2 atoms of oxygen, 1 atom of nitrogen, but since nitrogen is first, we don't use the prefix mono. Now, carbon monoxide is one where you use mono, but we use it for the second atom because there's only 1 atom of oxygen, so we use monoxide. Finally, one more example, carbon tetrachloride. Taking a look back, tetra represents 4, and since it's 4 atoms of chlorine, we'll use it for tetrachloride. All right. Now, acid salts. Acid salts are when hydrogen joins a polyatomic ion and reduces the charge of the compound by 1 for each hydrogen added. We're going to be adding the word hydrogen in front of the acid salt. So, for example, with a polyatomic ion CO3, if we only have 1 hydrogen, not 2, this is going to be HCO3 with a charge of -1. This is going to be indicated by the word hydrogen carbonate. Taking a look at another example, H2PO4 1-. This is going to be dihydrogen phosphate because we have 2 hydrogens in this compound. HSO4 1- is going to be hydrogen sulfate because we have the SO4 polyatomic ion but only 1 hydrogen. CrO4- has a charge of 2- and hydrogen has a charge of 1+. So this is going to be indicated hydrogen chromate. Finally, HC2O4. C2O4 has a charge of 2- and hydrogen has a charge of 1+. So the overall compound is 1-. This is indicated by hydrogen oxalate. Alright, finally, compounds when sulfur replaces oxygen. We're going to be using the prefix thio at the beginning of the compound. So, for example, H2SO4 or sulfuric acid will become H2S2O3, thiosulfuric acid. Literally what happens is one of the sulfurs replaces one of the oxygens in the compound. So we take out an oxygen, so this becomes from 4 to 3, and we add another sulfur. So it goes from 1 to 2. For example, SO4 2- or sulfate will become S2O3, thiosulfate. Now, the charges will stay the same, but we add the prefix thio, and we remove 1 oxygen atom, we add 1 sulfur atom. OCN cyanate will become SCN, thiocyanate. So again, the charge will stay the same, the name doesn't change, but we add 1 S, remove the oxygen, and add the prefix thio. So in this situation right here, the 1 oxygen is removed and 1 sulfur is added, even though there's no sulfurs to begin with. Alright, and that ends today's lecture. Next lecture is going to be focusing on chemical reactions and balancing them, so stay tuned.